Hello, welcome to my pipeline integrity video series. My name is Colin Scott. I'm an independent pipeline integrity engineer working out of Calgary, Alberta, up in Canada. Today's video, we're going to look at crack stability considerations. This is something that we don't necessarily think of as much as we should have. And those of us that are interested in environmentally assisted cracking that are subject to stable crack growth might have some interest in this. Today, we're going to walk through a fairly simple example of the crack stability considerations associated with a single edge crack. Now I'm going to assume that anybody that's watching this video has some interest in pipeline integrity and some experience, I hope, with crack management. So when we look at the fracture mechanics basics, we're going to look at Irwin's equation. So Irwin's equation defines the stress intensity factor K as being a function of Y, which is a compliance factor. That's a geometric factor that depends on crack depth and length and wall thickness. That stress intensity factor is going to depend on the applied stress, in this case sigma, and then square root of pi times the crack depth. I'm hoping that that's going to be an equation that some of you are quite familiar with. And we know from our basic fracture mechanics theory that the fracture criterion is that the applied stress intensity factor, if it's greater than the critical K1C toughness of the material, then we're going to get fracture occurring. That's a fairly simplistic way to look at things, but it gets us off on the right foot. So first of all, let's take a look at Irwin's equation, the stress intensity factor associated with an edge crack and with a back wall correction factor. So here I've got a simple equation. My Y compliance factor is 1.12, which is fairly common for edge cracks. And then I also have another term of the square root secant of the crack depth ratio. What that does is that defines how the stress intensity factor is going to increase as a crack gets deeper and deeper through a finite thickness plate. I'm guessing that some of you have probably seen this before, and we're going to be able to move forward fairly quickly here. So here I do a simple plot of that stress intensity factor. On the y-axis, I've got a normalized stress intensity, so I'm assuming a uniform applied stress of unit 1. And on the x-axis, I have the depth. In this case, I've gone from 0 to 10, assuming a nominal wall thickness pipe wall of 10 millimeters perhaps, and then the depth accordingly would be in millimeters. Now you see from the shape of this curve that when the cracks are shallow, on the left side of the curve, the square root of the pi times crack depth term dominates. And so we can see a fairly distinctive square root relationship there. However, as the crack gets deeper, the secant term comes into play and starts to increase that stress intensity factor up and away from the typical square root relationship. That curvature becomes quite important when we start thinking about crack stability. And I'll show you how and why. When you look at some more advanced theory behind fracture mechanics, you'll find that there's some fine print. We can consider crack growth as either stable or as unstable. In the case of environmentally assisted cracking with, say, stress corrosion cracking, some hydrogen cracking, or some hydrogen sulfide cracking, we can have a crack that's moving but not in a catastrophic fashion. That's considered stable crack growth. Most scenarios that we think of involve ruptures in which we have unstable crack growth. Now, the way that we can determine whether we have stable or unstable crack growth is to look at the K gradient, so the stress intensity factor gradient, with respect to crack depth, and compare that to the K1C gradient, the toughness gradient, also with respect to crack depth. Some of you might have seen this before. Typically, this approach is applied to strain energy release rates or J integrals for fracture problems, including plasticity considerations. Now, if we have a K gradient that is less than a toughness gradient, we would expect to have stable crack growth. And if we have a K gradient that's greater than the toughness gradient, we would expect to have unstable crack growth. And there's several things that we can think about in terms of the K gradient. If we have displacement controlled conditions, it's fairly common to have a low K gradient, and we know that under displacement controlled conditions, our cracks may well stabilize. In the case of unstable crack growth, we may have a K gradient that is propagating into an increasingly brittle material, which would then lower the toughness gradient and allow for unstable crack growth. So there are various combinations and permutations of K gradient and toughness gradient that we need to think of. If we're worried about environmentally assisted cracking, and we know that our cracks are growing in a stable fashion, we know that the fracture mechanics behavior is essentially defined by that upper equation. And that becomes a very, very important thing. If we know what the stress intensity factor gradient is for a given crack of a given depth and length and wall thickness and geometry, the fact that we've got stable crack growth means that we can infer what the toughness gradient is at the crack tip. And that can be quite useful. Now, the crack stability question is really a shade of gray. If you have a low K gradient, that's going to result in a more stable crack, which is generally better in terms of managing your pipeline integrity. But if you have a K gradient that's high, that means that the crack is less stable, and that's going to be more of a problem in terms of your pipeline integrity program. So that's something that we need to keep in mind. There are shades of gray involved here. Now, if we go back to our edge crack example, where we have an edge crack in a finite wall thickness, in order to determine whether we've got a more stable or less stable crack, we need to be able to take a differential of that particular equation. Now, I'm not smart enough to figure out how that combination plays out, so I went to an online resource and I found that there's a beast of an equation for the crack driving force gradient. I'm not smart enough to check out that this is 100% correct, but what I have been able to deduce is from the shapes of the different curves, it appears to be doing what I would expect it to do. So I'm going to keep my fingers crossed and move forward with this. Let's take a look at our edge crack example and see how the K gradient changes as the crack grows. So here we have a plot with the normalized stress intensity gradient on the y-axis, and we have the depth on the x-axis. And you see a very interesting shape here. When the crack is very, very shallow, less than 1 millimeter, less than half a millimeter, you get a very, very high stress intensity gradient. And that corresponds to the very start of the square root relationship that we saw before. But as the crack gets deeper and deeper, the stress intensity gradient decreases. So that essentially means that our crack is becoming more and more stable. Once our crack gets deeper and deeper to 4 or 5 or 6 millimeters, you see that that stress intensity gradient starts to increase again, meaning that we're going to have a less and less stable crack. So it's fairly interesting to me to see that our crack grows from a very unstable form to a more stable form to a less stable form during its propagation. And I'm not sure if any of you have seen a plot like this before, but it really reminds me of something that I've seen in the stress corrosion cracking literature. Here I have a figure from a PHMSA report from 2005. This was sponsored by PHMSA and its Technical Task Order 8, and it's a study of stress corrosion cracking. And here's a plot of what's often referred to as the bathtub model of stress corrosion cracking. Researchers in the field have found that fairly shallow cracks will grow with quite a high rate. As the cracks grow, they will slow down. And then as they get deeper and deeper, they're going to get higher and higher crack velocities until they ultimately have failure. This has been demonstrated in various ways by different people. And if we look at how crack velocity is changing as the crack grows, we'll see that it decreases. If I also look at a CEPA study done 2007, I get a very similar behavior. Here the bathtub model goes from a high SCC growth velocity to a lower velocity, and again to a higher velocity. Now, if you read the stress corrosion cracking literature, you'll find that there are several explanations for this behavior. People will look at the electrochemistry, the phenomenon that's going on at the crack tip, and how the chemistry is affecting crack growth. people will talk about hydrogen ingress and diffusion, hydrogen concentration at the crack tip leading to embrittlement of the material. You'll hear about anodic dissolution. Some people will tell you that as the cracks get deeper, there's a longer diffusion path for species to move along, which slows down the whole reaction rate and cracking mechanism. And you'll hear people talking about deeper cracks transitioning to more of a fatigue type behavior, which increases their crack velocity. I'm not going to explicitly comment on any of those different mechanisms, but I will say is that when I plot my DKDA against A curve, I see something that looks very, very similar to that bathtub model. And to me, as a fracture mechanics person, it just seems more than coincidental that things would play out that way. So I'm going with the observation that the bathtub model very similarly matches my, my crack stability expectations, just simply based on the K gradient. So think about that. I'm sure a lot of people will come up with reasons that that's not appropriate, but I'm gonna kind of work with that assumption to move forward. So let's take a look at how our stress intensity factors are going to change for different wall thicknesses of material. Here I've got a plot very similar to the one before, but I've included two more nominal wall thicknesses. In this case, a 5 millimeter wall thickness curve shown in red and a 15 millimeter nominal wall thickness shown in green. So we can see here from this plot that depending on what the wall thickness of our pipe is, we're going to get a different stress intensity factor for different depths as a crack propagates through a pipe wall. That's not going to surprise anybody. What we also want to do, though, is look at the crack stability considerations. If we take a look at the K gradient as the crack grows, we'll find that there's a substantially different behavior. We all have the bathtub type shape, but we have changes in stress intensity gradient for the different wall thicknesses that are quite dramatic. So now when we think about our overall fracture criterion of fracture will occur when the K is over the toughness, and crack stability is affected by the K gradient with respect to the toughness gradient, now we have two different things to worry about when it comes to understanding how our cracks are going to propagate and whether the crack is going to propagate stable or unstable. So what are the implications of that? We mentioned before that when we've got environmentally assisted cracking, we initially have some stable crack growth, and that could be stress corrosion cracking, whether near neutral pH or high pH in the oil and gas industry. We could have hydrogen sulfide cracking involving some stable crack growth. We could have some hydrogen cracking involving stable crack growth. So the various comments that I've put forward in the mathematics that's been put forward by the literature is quite relevant to the situation. What we learn is that the crack stability is a function of the crack depth and length and the component geometry. So I have to ask the question, are the laboratory tests that are being done by various researchers around the world, are they necessarily appropriate for pipeline conditions? I don't recall seeing papers where crack velocity was discussed in terms of crack stability considerations and specifically with respect to K gradients. I also need to ask myself, can the crack growth rates be inferred from the stability considerations? Is it possible to look at different crack geometries, different crack depths, different crack lengths, and different wall thicknesses? And from the stability considerations, is it possible to infer what the crack growth rates would be? And then also, we need to ask the question of, can material toughness gradients be inferred from the stability considerations? And if we can infer the material toughness gradients, does that give us any insight into how the crack growth mechanism is occurring from an electrochemical perspective? A few things to think about. I'm just going to give you a chance to sit and chew on that. I'm sure people have various philosophies on how the bathtub model occurs. I've made this observation that the K gradient for our basic crack seems to change in the same sort of shape as the bathtub model, and it's got my head thinking in that direction. Whether it's right or wrong is is for all of us to figure out as we go forward. I hope it's given you something to think about, though. In the next video, what I'm going to do is I'm going to extend some of these arguments from the single edge crack philosophy into a periodic crack array, which would be more typical of stress corrosion cracking colonies in oil and gas pipelines. That becomes quite a bit more complicated and gives us quite a few more things to think about. Hopefully you've enjoyed this video and I've given you something to think about. If you have any questions, please feel free to post them on YouTube or on LinkedIn, and I'll try and answer them if I can. Thank you very much for your time. Have a good day.